AP Physics 1, Unit 4, Workbook, Work and Energy. Activity J, Impact of Mass on Conservation of Energy. Read the scenario along with me. Please remember to pause or rewind the video as necessary. An apparatus to determine the coefficients of friction is shown to the right. The box is slowly rotated clockwise, or rather, counterclockwise, when it creates an angle theta with the horizontal. The block of mass m starts to slide, and at this instance, the box is stopped from rotating. Thus, at angle theta, the block slides at distance d, hits a spring of force constant k, and compresses the spring at distance x before coming to rest. Part A, draw a qualitative energy bar graph that represents the energy of the block earth spring system at the locations indicated. Okay, so the locations indicated are the initial position, which would be up here. When x equals d, that means right there, right before the block begins to compress the spring, and then right here when the block has fully compressed the spring. I'm going to label this position A, B, C, just to give it some relevance on the chart. Let's go to the actual picture, and let's talk about the energies at these different spots. So the energy at position A, well, there's no kinetic energy at position A because it starts from rest. There is gravitational potential energy, so we'll write mgh, the equation for it. Since the spring has not been compressed yet, the spring potential energy is 0. At this moment right here, position B, you have kinetic energy, so we'll write its equation 1/2 mv squared. We have a little bit of potential to fall, not much, but a little bit, so I'm going to write mgh. The reason why is because the block is going to fall from this height to this height right here as it fully compresses the spring. I'm going to take 0 potential energy as the lowest point it gets to before the spring is fully compressed, which means the block does have a tiny little bit of potential energy right when it starts to compress the spring. We'll talk about that in a minute when we get to the bar graph. Since the spring has not yet been compressed, that's at point B, and the spring potential energy at point B is 0 only because, like I said, this spring has not been compressed yet. And then now let's talk about this point right here when the block has fully compressed the spring. We'll call that position C. You have no more kinetic energy because the block comes to rest. The gravitational potential energy has now gone to 0 because that's the lowest point in the problem. But you have complete and full spring potential energy, so I'm going to write its equation 1/2 kx squared. So these are the energies involved at the different locations. Let's take a look. Now, if I'm going to qualitatively start with anything, I'm going to start by assuming that my total, I have 4 different bars here, 1, 2, 3, 4 bars. And what I'm going to do is I'm going to arbitrarily start off with the fact that, well, we have nothing but mgh to start with. So I am going to make a bar graph that goes 4 units high. I'm going to go all the way to the top just to give it some comparative relevance with other parts along the way. So there's my initial bar graph for the spring potential energy. And notice that it's 4 units high. Now, if total energy needs to be conserved, that means all of my bars have to add up to 4 units high, no matter what energy it becomes, okay? Now, as one more thing I forgot to mention, since you're trying to essentially use this to figure out, determine the coefficient of friction, that means, of course, that there is friction during the slide, specifically the work done by friction during the slide. Which means the work done by friction will reduce the mechanical energy. So the mechanical energy will go down from 4 bars to less than 4 bars, and that extra energy now becomes what's called thermal energy. Friction is now transforming that mechanical energy into thermal energy of the surrounding air molecules. Well, since once you hit the spring at position B, your potential, so here's your height right here when you hit the spring right there. And you can see once you fully compress the spring, there's not a whole lot of height left relative to where it started. So what I'm going to do is I'm going to go ahead and say that my potential energy, which I'm going to still use in black, is going to be that much, about 1 unit high, because there's not much height left to fall. I'm going to say, since there was a loss of mechanical energy, I cannot very well say that my kinetic energy cannot be 3 units high to add up to 4, because that would indicate no loss of mechanical energy. But friction caused there to be a loss. So I'm going to have to make that kinetic energy shorter. I'm going to make it about 2 bars high. Okay, so now the mechanical energy went from 4 bars high in position A to only 3 bars high. So the remaining 4th bar would be the E therm, or thermal energy. Just like that. Notice I have no bars under US for spring potential energy because the spring has not yet been compressed at that point. Okay. So now what begins to happen at this point is the remaining potential energy is going to convert itself into spring energy. So I'm going to list that one. Okay, so I have my spring energy going the same. So the remaining potential energy I lose right here becomes the spring energy right here. Now, if the spring potential energy is 1 unit, then the 2 units of kinetic energy is going to convert to thermal energy. So plus the 1 unit of thermal energy that was already right here, that would bring this up to about, what, 3 units of thermal energy? Part B. In a subsequent experiment, a second block of mass 2m is subjected to the same conditions as the original block. This new block is made of the same materials as the first block. Indicate how the values below would change in the second experiment. So, talking about velocity. So how does velocity change? Well, let's examine from A to B, just in this chunk right here. Energy initial equals energy final. Now, initial would be A and final would be B. So you can see we go from mgh to mgh plus 1/2 mv squared plus the work done by friction. Let me add that in there. So that's mgha, mghb. I'm just going to add this. Each part, and plus. There we go. Oops. There we are. Okay, a little typo on my part. But what we have there is we have the gravitational potential energy converting into kinetic and potential energy at point B, and the work done by friction is also reducing the mechanical energy on that back end, as we saw in the bar chart above. Now, doing a little bit of conversion, the work done by friction would be the force of friction times distance, which is mu times normal force times distance. Now, on an inclined plane, normal force is equal to mg cosine theta. So you can see how mass cancels from all four terms, which means speed is independent of mass. So we can summarize that by saying in the first part, from up to x equals d, that means until the block compresses the spring. If there is more mass, then there is a greater friction force and a greater gravitational force component. Little typo there. Forgot about that. But the coefficient of friction does not change. The greater gravitational force is balanced by a greater friction force. Thus, the mass increase does not affect the speed of the block hitting just before the spring. Okay, and again, another way to describe it is, mass simply cancels algebraically from each and every term. Therefore, speed is not dependent on mass. Okay, how about the distance the spring is compressed? Although the mass does not impact the spring just before the block impacts the spring, it will impact the distance the spring is compressed. Let's think of it this way. Spring energy does not have a mass component. If you have twice the mass, then you start with twice the mechanical energy, which means you end up with more spring energy. Now, you are losing some energy due to friction along the way, but what's going to happen is, since we have a greater initial energy, you're still going to have a greater final spring energy, which means you will end up compressing the spring a little more. There'll be an increase in that. So the 2M block will have more gravitational potential energy in the beginning because of the greater mass, and thus a greater final spring energy. The spring will have to compress further with the same spring constant because of the greater initial energy.